Hello there, YouTubers. Today we're going to look at indeterminate forms and L'Hopital's rule. L'Hopital's rule will be one technique that one might use to evaluate indeterminate forms for limits. Alright, first what we want to do is analyze the numerator and denominator separately of this problem. So let's see, as x goes to 1, where does the numerator go? The numerator goes to 0. X cubed minus 1 is 0. As x goes to 1. Where does the denominator go? The denominator, again, we're examining these separately, goes to 0. So what we would say is this has 0 over 0 form, and this is an indeterminate form, meaning once simply analyzing that it has 0 over 0 form, you can't determine the limit on that basis alone. That level of analysis isn't enough to determine what the limit is or isn't. So first, let's identify the form that we've had. Now we can apply L'Hopital's rule. So L'Hopital's rule will apply when we have 0 over 0 form. So here we have the limit as x goes to 1. Now let's put here LH, just some sort of notification that we're going to apply L'Hopital's rule on this step. And so now we take the derivative of the numerator as our numerator, derivative of the original numerator, and then we take the derivative of the original denominator, which is just 2x, and L'Hopital's rule tells us that if this limit exists, which we haven't determined yet, then it has the same limiting value as the original problem, and that's what justifies the placement of the equal there. So let's see what we have. Now, basic Cal 1, one of the first limit theorems, which says you can think of it as cancellation in terms of the limit. So this is 3x over 2, and we evaluate this just by functional evaluation, and that's just 3/2. So this limit, the limit of the ratio of the derivatives exists, namely it's 3/2. So L'Hopital's rule tells us two things. The original limit exists, and it's in fact has the same limiting value. So that's our first application of L'Hopital's rule. Now recall, just as a side note, our Calculus 1 classical method would be just where you don't have L'Hopital's rule is you just solve the problem by factoring. So here's an alternative, more classical method. Nothing wrong with this except that we're studying L'Hopital's rule today. So remember, it may not be the only way to go, but L'Hopital's rule is very powerful and quick. Notice it was probably done with this problem faster in L'Hopital's rule, even with the explanation, than it is here because this is factoring. Still fairly simple to factor. And now, same thing, we evaluate by plugging in. So we get the same limiting value. Of course we had to, because that's what the limit is. And here's the classical technique compared to the more powerful, so to speak, Calculus 2 technique. That's typically where it occurs in most college level courses, which is L'Hopital's rule. Alright, let's look at our second problem. Is very similar to the other one. Let's analyze our indeterminate forms by investigating the limit of the numerator and denominator separately. So here in the numerator we have the limit. Here in the numerator we have the limit is going to 0. In the denominator we have the limit is going to 0. 1 minus 1 is 0. So again, this function has the indeterminate form 0 over 0, which is good. So we can apply L'Hopital's rule, attempt to apply L'Hopital's rule immediately. So let's see what we get. So again, let's just put something here to say we're about to apply L'Hopital's rule. Now remember, this is not the quotient rule. There's no connection to the quotient rule. You're taking the derivatives of the numerator and denominator separately. And again, and by the way, the reason I gave you this problem, when we analyze what a calculus 1 technique would be, as I did in the last problem, let's go ahead and bring the constants out. 70 over 20, which reduces to 7/2. And now this just cancels, giving me x to the 50, however you like to write it. Alright, and now x to the 50 as x goes to 1 is 1, so this is just 7/2. And very simple, straightforward application. Now, when we did method 2, who would want to factor that? Even if you know the factoring formulas, which I do, there's still that x to the 70 minus 1 is x minus 1 times x to the 69 plus, there's a lot of different terms in there, and plus x to the 68 plus x to, that's a lot to write down. And the same for this one. That's too much to write. Not too much to write, we could do it, but it turns out it's be much more difficult to do. L'Hopital's rule is much faster here. So we have a nice, elegant solution to a problem that would pose a little challenge to us if we tried it classically with algebraic techniques in terms of factoring. Okay, let's try another one. First thing we want to do is analyze the form, and I'll do that kind of as we're going to go. The numerator goes to 0, sine of 0 is 0, the tangent of 0 is 0, so this has 0 over 0 form. So I'm going to skip writing it out for this problem. This has the form 0 over 0. We could write out the limit separately to be a little more formal. Alright, so now we're going to try to apply L'Hopital's rule. And now here we have to remember the derivative. We have a chain rule problem. But what's the derivative of sine of 3x? Well, it's the cosine of 3x. Now we have the chain rule, times 3. What's the derivative of tangent of 4x? Well, it's the secant squared of 4x, the chain rule, times the derivative of the inside, which is 4. So the first thing, let's just remove these constants, and let's see what we have. And at the same time, let's just recopy. Now it turns out here we have to reset our process and think about what's going on, but both of these functions are continuous at 0 and the denominator is not 0, so we can evaluate this using functional evaluation. This is just the cosine. What's 3 times 0? That's just 0. And then we have the secant squared of 4 times 0, which is just 0. And I think we all recall the cosine of 0 is 1, and so is the secant squared of 0. So that's just times 1 over 1. And this is just 3/4. And that's our value, our answer. And again, L'Hopital's rule was applied here. So let's review the theorem. The limit of the ratio of the derivatives exists, and it's 3/4. Therefore, L'Hopital's rule tells us that the original limit exists, and it has to have the same limiting value. So it's 3/4. Okay, let's look at this one. Now, what's its form? Alright, so the numerator, as x goes to 1, we get the square root of 5 minus 1 minus 2 times 1, which is 0. Square root of 5 minus 1 is the square root of 4, which is 2. 2 minus 2 is 0. The denominator is simply 1 minus 1, so it's 0. So what form do we have when we look at these separately? 0 over 0 form. So that's the first step. Identifying that we have 0 over 0 form or infinity over infinity. That's another case that we haven't discussed yet in this video. Alright, so now we can apply L'Hopital's rule. Now let's recall, what is the derivative of the square root of 5 minus x? Well, let's do it on the side here. The derivative, and I'll write it as an exponent, the derivative of the square root of 5 minus x is 1/2. Recopy the inside, decrease the exponent by 1, and then times the derivative of the inside. That's the chain rule. So that's the derivative of this right here. So let's go ahead and put that in, since we computed that on the side. Again, so when you do L'Hopital's rule, since it involves a statement of derivatives, you need to brush up on your Calculus 1 derivatives. Okay, so this is the derivative of the denominator is just 1. So now we can achieve this by functional evaluation. So the answer is, we can just evaluate now. So this is 1/2 times 1/2 minus 2, which is equal to 1/4 minus 2, which is 8/4, negative 7/4. Check that. 5 minus 1 is 4. Now this is negative 1/2, so that's the reciprocal of the square root. So the square root of 5 minus 1 is the square root of 4, which is 2. This is 1 over 2. So 1 over 2 times 1 over 2 is 1/4. 2 is 8/4. So what is our answer? Negative 7/4. Alright, so there's our result. And the answer is negative 7 over 4 by L'Hopital's rule. So here, we don't have a numerator, nor do we have a denominator. So let's look at these two pieces, and if we analyze them separately, notice the limit's going to pi halves. So what this piece is the simpler of the two, that's certainly 0. Now what about tangent? Do we recall what happens with tangent at pi halves? Well, strictly speaking, the limit's undefined. But let's look at the left and right hand limits separately. Let's consider the graph as well. So let's do the limit from the right. So this is equal to negative infinity. Let's look at the limit from the left of pi halves. And this is equal to infinity. Basically, here's pi halves as our vertical asymptote. Let's look at the tangent function. Alright, so the limit as x goes to pi halves from the right goes to negative infinity, as I've shown. And the limit as x goes to pi halves from the left goes to positive infinity. Okay, so notice then, even though we, at some level, the full limit is d and e, what do we see when we evaluate the left and right-handed limits? Each are going to infinity. So what we'll say is, in our analysis of this form, we're going to say that it's 0 times infinity form. That's how that analysis will go. And now what we need to do is take the reciprocal of one of the two pieces. Now a lot of times we'll do the algebraic piece, but the trig function has a nice reciprocal. So we're going to rewrite this function in an equivalent way, except for value close by pi halves, we should say. Okay, now analyze that for a moment. And do you see what I did there? So really, since you're writing it in the denominator, you take the reciprocal. And what is the reciprocal of tangent? Well, when both functions are defined, it's cotangent. And that's what I had a moment ago. All right, so now we need to reset our process and analyze this form. Now again, this is a fraction, which is what we want. It's a quotient, it's a ratio. So this has 0 over 0 form. Cotangent goes to 0 as x goes to pi half. So this is the form for which it's appropriate for us to apply L'Hopital's rule. So let's now do that. Let's look at these derivatives separately. Once again, we have to remember some easy derivatives of trig functions. What's the derivative of x minus pi halves? Well, that's just 1 with respect to x. What's the derivative of cotangent? Negative cosecant squared x. And now again, this function is in fact continuous at pi halves. So we just evaluate by functional evaluation. I'll write the negative up in the numerator, just as a matter of style. And it's the cosecant squared of pi halves. Remember, cosecant is 1 over sine. So what's the sine of pi halves, which is 1? 1 squared is 1, so this answer is just 1 in the denominator, so it's negative 1. And that is our answer to the limit. So notice here, we had 0 times infinity form. We had to employ some algebraic and technically trigonometric manipulations to get it into a quotient, so we could then get the appropriate indeterminate form, namely 0 over 0, so that we could apply L'Hopital's rule. Sometimes you have to apply L'Hopital's rule more than once. So first let's analyze our form. As x goes to infinity, notice we're having, at least in this video, the first limit at infinity. So as x goes to infinity, well, x cubed goes to infinity. And of course, as x goes to infinity, e to the x goes to infinity. So we have here infinity over infinity form. So what we would say if we were analyzing these fully and separately, as x goes to infinity, x cubed is infinity. And as x goes to infinity, the denominator, which is e to the 2x, tends to infinity. And that's what gets us our form infinity over infinity. Let's move this out of the way. Okay, so now L'Hopital's rule says we can find the ratio of the two derivatives and see what happens. So what's the derivative of x cubed? 3x squared. What's the derivative of e to the 2x? 2 times e to the 2x. And again, let's analyze. We have the numerator still going to infinity. The denominator, of course, didn't change except as a factor of 2. But remember, these can be moved outside, so I'm not even considering those. It goes to infinity, the denominator. So we still have an indeterminate form, infinity over infinity. So you may think, hey, what's going on here? Well, it got better. The degree of the numerator is smaller. So we're achieving some progress. I'm just going to leave the constants in. 6x over 4 e to the 2x. Okay, once again, let's analyze our form. Still infinity over infinity. So we're going to apply L'Hopital's rule one more time. Not once, not twice, but in fact thrice. Now I'm going to also simplify this 6 over 4. It's 3/2, and I'll go ahead and move that out for convenience. What's the derivative of x? That's just 1. And again, you have 2e to the 2x. So finally, we've broken free, so to speak. Now the numerator is constant. It's going to 1. Some people say it's not going anywhere. It's staying 1. And the denominator is going to infinity. Now by the squeeze theorem, then we have the numerator is bounded. But it's a bounded function. The denominator is going to infinity. So this whole limit by squeeze at infinity is 0. So let's come down. So this is 3/2 times 0, which is that limit. And finally, the answer is 0. So, by L'Hopital's rule, this limit is 0, and therefore, by L'Hopital's rule, rather, the original limit is 0. So, can you apply L'Hopital's rule more than once? Yes. We did it, in fact, 3 times. And had this been x to the 7th, we would have done it 7 times. So here's another indeterminate form that's a little different. Let's analyze each piece separately. Let's look at the first factor. As x goes to 0 from the right, well, of course, x is going to 0. And now as x goes to 0 from the right, and that's why we have to have from the right here, because the domain of the natural log function is the positive real numbers. So this is negative infinity. So our form, we don't say 0 times negative infinity. We just simplify it rather and just say this is 0 times infinity form. So again, we need to do the same piece that we did before. This is not L'Hopital's rule. We're just rewriting it algebraically first. And again here, what you want to do is we want to take the reciprocal of one term and place that in the denominator. Best to use the algebraic term. In this case, even though in the trigonometric problem we didn't, it's just the way the derivatives work. If you consider it as x over 1 over the natural log of x, which you would then have 0 over 0 form here, but it's this derivative which wouldn't be nice. The natural log would reappear and be due to the chain rule. So this derivative is a little simpler once we hit it with L'Hopital's rule. And before we can do that, what do we have to do? Analyze the what? We have to analyze the form. We've rewritten it intentionally. So now this has form infinity over infinity because, let's just look at the denominator. It's the only one that's changed. The limit as x goes to 0 from the right of 1 over x is infinity. So again, top is going to infinity, negative infinity, as we said earlier. The bottom, and now the denominator goes to infinity. So this is infinity over infinity form. Now we do L'Hopital's rule. What's the derivative of the natural log? 1 over x. And what's the derivative of 1 over x? Negative 1 over x squared. And technically we need parentheses there. So let's rewrite it here. Let's do our algebraic manipulation. Take the reciprocal of the denominator. This is just negative x. And again, this function is continuous at 0, so we evaluate by functional valuation. And so that is the answer to our original problem. And if we look at the graph, again, and we see that what you can see right here, as x is going to 0 from the right, the function goes to 0. Well, thank you for watching this video, which is part 1 of our L'Hopital rule series. We've done 3 of the indeterminate forms today in this video: 0 over 0, infinity over infinity, and 0 times infinity. In part 2, we will do infinity minus infinity, 0 to the 0, and 1 to the infinity as the 3 remaining indeterminate forms. So I look forward to seeing you there. Thank you very much.